where I'm trying to recall where I was. I had the series in the Libra, I had the Cartan, I had a system of positive roots, and to all this I associated this category. Oh, and I guess I proved that that is finite length. Every object is finite length. It's I think pretty clear that it's Abelian. And okay, and and now it's pretty clear too. I think that it will decompose. How should I put this? Let's write in brackets that it will be the sum of all maximal ideas of the center of something I call chi, and this will be defined as the objects of O, which are killed by some power of the maximal ideal in the center chi. So those were central character, and you see, I mean, well, it's not possible to make a direct sum of abelian, a direct sum of categories. Sort of doesn't make sense. But in this case, well, you know, you could take just inside the product of categories. This always exists. The tuples where almost all entries are zero. So it's not the co-product of categories, yeah, but let's just allow ourselves to write it like this. Okay, and these guys are sort of much better because they have only finitely many simple objects, right? And see the irreducible objects of chi. This is I want to write it to this side. Irreducible object of chi. This is just the L of x dot lambda. X is in the Y group. Well, I should in fact write that it's the L of lambda, where the Harish-Chandra homomorphism maps lambda onto chi. But it's also this is the same one W dot orbit. Okay, and now I want to have a look at these categories of chi. How they look like. I mean, okay, there's one special case. There's one special case where sort of most singular. This is sort of the usual terminology, which means that chi is psi of minus rho. So in this case, the irreducibles of this category of chi, there's just one. Yeah, it's the Fermat module with height grade minus rho, because this is fixed under the Y group. This guy. So this is why it's called singular. No? Most singular. The more elements of the Y group fix the parameter, the more singular it is. So there's just one simple object. because the wide group orbit is just one element. And so we can deduce that the category of chi is isomorphic, equivalent to the category of finite dimensional complex vector spaces. Namely, if we have here an object, we just associate it with the highest weight, n minus rho. So it's just direct sum of this one Werner, that's best. Okay. Now there's the next case. If let's say the non-integral case, non-integral but regular. This is if so C minus 1 of chi consists of two elements, say lambda and S dot lambda, yeah, which is mu. But the difference of these two is not in the root levels. So this is the subgroup generated by the roots of H dual. So in this case, this irreducible object of O chi, there's still only two. There is the Werner module, and the other Werner module. And these see the point is that the difference of these weights is not a root. So there is no way to have, there's no homomorphism from one Werner module to the other. So there's only one simple subquotient which could possibly appear here. And so we have two simples which have nothing to do with one another. And so this in this case, the category O chi is isomorphic, equivalent to two copies of finite dimensional C vector spaces. And just every object is a direct sum of these two Werner modules. There are no homomorphisms between the two. So it's just, I take to say, the highest weight space and the other weight space, and that's it. So also very trivial situation. So we see that most of the time we are in very trivial situations. The category has not so much interest. But then there is a lot of the interesting cases. Which is pi, it's the annihilator of the trivial representation. So psi of 0. So in this case, the irreducible representations of O. Yes, there are two guys. There is L0, which is the trivial representation, and there's the Werner module, the simple Werner module of highest weight minus 2 rho. All the simple guys they are there, and so I can try to draw a picture of how an object of this block of this part of the category O looks like. Namely, here we have a sort of the weight space of weight minus 2 rho, and here we have the weight space of weight 0. And then below, the weight spaces have to stay all the same. Yeah, because these are the only two simple subportions. So downstairs it's all isomorphism. Yeah, downstairs it's all isomorphism. But upstairs something can happen. And now we see that what can happen. I mean, we have here these two vector spaces, and we have a map E, which gets this vector space up here. And you have a map F, which takes this vector space down here. And here, and now the theorem is that this is all there is to it. Namely, we have an equivalent now from this block here. This is equivalent. Well, to say, I don't know, V representations of the quiver. So one arrow up, one arrow down. Oh. Yeah, we have this quiver, and we want morphisms from this quiver to the category of finite dimensional Z vectors. And we don't want them all. We want, well, we have some relations between these two arrows. Namely, if we go down and up again, this should be the same as going up and down, right? Because the commutator of the two is h, and h is 0 here. So, but going up is already 0. Going up and down is also 0. So we need the relation that going down and going up again is 0. Right? So E is going up, the arrow going up and arrow going down. So we take two finite dimensional vector spaces and two linear nets, and then such that these relations are satisfied. And then this category, at least we have a functor from category O, trivial block, to this category. And this is even an equivalence. This is even an equivalence of categories. I mean, you can give explicitly an inverse functor. Let me explain how to write down the inverse functor. Namely, if we have such let's call this point here P, and this point here Q. Yeah, it's an arrow, two arrows, and a quiver. Yeah, two arrows, 2 points. So we should, if we have here a representation of this quiver, we should associate to it V of V plus V of U. And this thing, we should make it into a representation of the Borel B. Yeah, because E is just given to us. So and we know how H should act. Yeah, H should act with weight -2 here, with weight 0 here. So we can declare this is a representation of B, and we induce it up. And then we get something a bit too much. We get a module with a Werner flag only. Yeah, if we take a finite dimensional representation and use it up of Borel, we get too much, and we should divide out something. Yeah, we should divide out the submodule generated by P is downstairs, so we should have F V tensor should we divide out sort of the obvious thing. So one tensor F uh, F W 0 minus F tensor 0 W for all W and V Q. Well, you have to think about a bit about it. I'm not supposed to understand it on the spot, but here sort of this we have a map F from here to here, and this should turn out to be the correct map F. I mean, up to now we have the minus 2 rho by space double. We sort of skip it off. Well, whatever. So this is an equivalence of categories with this category of representations of the quizzle. And now we can try to look at the indecomposable objects of this category. I mean, I have to say that this kind of thing, yeah, this was very much sort of the origin of this whole quiver business. Yeah, I mean, there's an old paper by Gelfand, I think, about quivers and indecomposable representations of the Lorentz group. And okay, I will discuss why this is indecomposable representations of the Lorentz group in some way. And then they're given by some representations of quivers, and then people started to look at these representations of quivers and so on. But now let's see. In our course, our case finally very simple. So I want to know what is indecomposable. The thoughts of me. So, well, I mean, what do we have as representation of this quiver? Yeah, I mean, we have C and 0, and the methods are evident. This will correspond to a representation where the minus 2 row wave space is of dimension 1, and the 0 wave space is of dimension 0. So here we have got the Werner delta. Delta minus 2 rho here, which is simple. Then we have a 0 mapping upstairs. Downstairs. Well, this is just a simple representation. So L of 0, which is the trivial one-dimensional. Then we have the C upstairs and the C downstairs, and here the map 0, and here the map identity. Here the map identity is media, and here the map 0. This is the Werner module with high space 0. Then we also have that here the identity goes up and 0 goes down. This is an object still to be discussed. So I write another object. So didn't discuss it. And then there is a last possibility. We have a C2 down here and a C up here. And one of the maps kills this guy and maps this identity here. This identity here. And the other of these maps project maps into here and well, again, Yeah. So then going down and going up again is 0, but otherwise it need not be. And this is sort of the most complicated. It will be the projective cover of the trivial representations to be discussed later. And that's it. So in a way, the situation is pretty cheap. Yeah, we have 5 indecomposable objects, and then there's some Krull-Schmidt theorem. Every object of this category is just a direct sum of these 5 guys. Okay, very good. Yeah, not so complicated. But now it's really sort of when you go away from SL2, things screw up considerably. And well, and then the next question is, okay, now this is the indecomposables of OC plus. And then what I did not discuss at all, I mean about the other, I mean there are these other categories, yeah, where we have n rows and n is some natural number, yeah. Yeah, I had just the trivial central character, but all these categories, in fact, they are all equivalent to OD plus by something called a translation factor. And this is also something I still have to explain. But modulo this, we now have a complete understanding of category O, at least I said 2. Okay. Okay. Now let me discuss this guy. And then let me discuss these guys. And then maybe translation factors. So I have a program. Okay. That's so I want to explain duality. The point is that there's a duality on category. So this will be in factor from O to O of O's, pattern equivalence, duality. And it's constructed as follows. I mean, well, if you have a representation, then you can take the contract region. Well, now we have already the first problem. Yeah, we have the first problem because this Werner module is, say, the direct sum of weight spaces, and then it will become the product of the duals of the weight spaces. Right? And so this is much too big. So the first thing is I make a circle here, and I just take only the sum of the duals of the weight space, just by definition. And then the next thing is so this will be now a sub representation. Yeah, so this is Soergel dual, which is a sub-representation of M complete dual. But there's another bad thing, namely that the dual of a weight space will be a weight space with a negative weight. So a highest weight module, like the Werner module, will get transformed to a lowest weight module, yeah? Which is not what we want. So the trick to cure it is to still apply twist this representation with an automorphism of the Lie algebra. And the automorphism, the trick is, there exists an automorphism of the Lie algebra. This is called Cheverly automorphism, which restricted to the H is minus the identity on H. And this is called Cheverly automorphism. Cheverly automorphism. And I don't know. I think for GLN, it's just take minus transpose. That's also why tau is a good letter. And now, because it's minus on the Cartan, it will sort of turn the weight spaces up down. Yeah. So now this is a pretty nice factor. And since we know already everybody of category O has finite length, it's clear it will make category O to itself, and the simples will just stay with the same simples. Yeah. And if we apply this twice, it's the identity. So all this is now pretty clear. So let me write it. So L lambda gets mapped to L lambda. Okay. Let's be careful. The dual of L lambda is isomorphic to L lambda. And D squared is isomorphic as a factor of the identity on O. Very well, and that's it. Well. And then this thing here is just defined to be the dual of the Werner field. Also for general lambda. Okay. So this is this thing. And now comes the next thing. Now let me try to fix. I have to avoid. Okay. And the next thing is these guys here. This is the projectives. So so let me discuss it here. Yeah. So there is a theorem. That this category O has enough projects. Okay. And that's a bit a question of whether I should prove it for you. I cannot prove everything, yeah. So maybe this maybe I will not. That's a pity, though. But what can I do? So I claim this has enough projective objects. maybe say something about it later. And there's more is true. Each projective has a Werner effect. So a filtration where all the subfunctions are Werners. And the last thing is like this. Projection of a projective on Werner module such that E is projective and the kernel of this projection has a Werner flag, subquotients delta mu or mu lambda plus some positive roots and u none. So here I use this notation for generated as a monoid. Okay, so this is sums of positive roots. And now that I wrote such a detailed thing, maybe I should at least say a little bit how it's constructed. Otherwise, it's so I'm so unhappy myself. So because the construction is not so terribly complicated. So this is maybe a construction. Namely, what we should do. Well, we have this d lambda tensor u of b u of d. This is our Werner model. And now what we do instead is we take C lambda tensor u of h, u of b, and then we truncate this. So we skip all weights which are in this. This is essentially the developing algebra of B. Well, not quite. And we take a part of it and then chuck it off. And so U should be a sum of positive roots sufficiently. Okay. And then this guy, you see, this is then a finite dimensional module of the Borel. And then this guy, we introduce it up again. So, U of B. And then we project onto the central character of lambda. And then this sort of naturally goes down here. And then one has to argue a bit that such a construction would sort of stabilize if we take U bigger and bigger and give a projective object. And okay, and so on. But I think it's at least the construction. The construction shows that why it's clear that this whole thing admits a Werner plane, right? Because if I have here a finite dimensional representation of E and I choose it up, then this guy has a Werner plane. And here the projection just kills some part of the subquotients which are sort of not of the core-central character. I should say that I didn't maybe make it sufficiently explicit. I have this decomposition into O chi, and to this decomposition corresponds this projection functions, which are exact functions, just taking sort of the chi generalized eigenspace corresponding to the central. Okay. So I don't want to give all the details here. But then so it has enough projective objects, and then there is some general nonsense which tells us, I can maybe know this. That we have a biject indecomposable projective object or the factor isomorphism. They are in rejection to simple objects of O. If we have an indecomposable projective object, then it has a unique simple quotient. Simple. And this is just always the case if we have a abelian category and every object has finite length and there are enough projective objects, then this is true. So for category O, it's true in particular. Okay, and the other way, if I have here some simple L lambda, then this guy is called the projective cover or the indecomposable projective cover of L lambda. And this now explains what this is. So this is the indecomposable projective cover of the simple wrong. This is the indecomposable projective cover of the simple Werner model. Because, well, I mean, you can see it in this quiver picture, yeah? If you think of this quiver category and you want to know what, I mean, the simple representations of such a quiver is just the edges, right? Here are two simple representations of the quiver. This simple representation. And the simple projective cover of this, you have to take all paths arriving at this as an endpoint. This is the way it has to be said in the quiver picture. And okay, this is a quiver with relations. So we can only take paths which satisfy the relations. And so, yeah, okay, you can take the identity path, this path, but the next path already would be killed by the relation. Because going down and up has to be zero. And so in this way, we see that this has to be the projective cover of the simple dom. Okay. Okay. And now the next thing, which was another sort of in fact the first sort of serious theorem about category O. This was by Bernstein. I mean, this whole category, yeah, it's very much a work of Bernstein and Gelfand, and a lot of what I tell you is their papers, and there is something called BGG reciprocity. And this stands for Bernstein, Gelfand, and another Gelfand-Faber and Gelfand-Zahl. And it tells us that the multiplicity of Wörmer inside the antidominant projective, inside the projective, an indecomposable projective. Yeah, this is an indecomposable projective cover of L lambda, and so this means Wörmer flag multiplicity. Flag multiplicity. This is the same thing as the multiplicity of the simple inside the Wörmer. And this is here the Jordan-Hölder multiplicity. And this is sort of the BGG reciprocity. And I mean this was sort of the first. I mean, in a way, the whole category O was built to satisfy this thing. In a way, it's a slightly artificial category, but this formula is so beautiful that it merits, and it is an analog of. I mean, there's something called Brouwer-Nesbitt reciprocity, which you might know if you read Serre's book on linear representations of finite groups. and this is the following phenomenon, that if you take the characters of a finite group of a positive characters, then this is an abelian category, and there's enough projectives. And so you also have the indecomposable projective covers of the simple objects. So these P lambdas exist, and the simple object exists as well. And what plays this role of Wörmer modules is those representations of a finite field, which come from irreducible complex representations. And then you choose a Z lattice, which always exists. And then, maybe over a number field, you have to be a bit careful, but you reduce them to characteristic T. And then you get not well-defined objects, but their characters are well-defined. And then we have the same formula. which is called Brauer nested reciprocity. And so they try to mimic it. And this is where it comes from. And now it will be an intermission until 1527. Pause. Okay, let me maybe move on. And I mean, right. There's something which we come later, but let's just explain it again. I mean, suppose say O, say A, is a C-linear abelian category. I have enough projectives. Finitely many simples. Many simples. And every object has finite. No, finite. If we have such a thing, then we know that A is equivalent to A modules, particular of A modules, finite dimensional A modules for a complex algebra of finite dimension. And we can even, there are several complex algebras of finite dimension which have the same modules category. This is a Morita equivalence business. But if we assume that A modulo, the Jacobson radical of A, would be just the product of copies of the ground field, then this algebra is unique. And so this category here, this category OK satisfy all these properties. So they are in fact described as finite dimensional algebra.
You assume that the unspaces are finite dimensional?
What one?
You need to assume that the unspaces are finite dimensional?
Oh yes. Thank you. You're absolutely right. So I need the endomorphisms of the simple objects are just simple. Are just very much so. And so this is not an idea. This is important. Otherwise, it's all wrong. What I tell you, because I could take modules over a field extension of C. Right. But we're not. Yeah. And yes, so it is of this type. And the indecomposable projectives, they correspond to these A1x. And 1x is this here quote by the radical. I assume it's just a product of copies of the field, and the algebra is called basic. the idempotents in here, they correspond to the simple representations. And so there's a whole big translation business, yeah? And in this business, this is the projectives. And now I can also write for you the algebra effect. I mean, what would be the in case of SL2, yeah? Of A Z class. Yeah, this I have this question. No. I have said that this is representation of a quiver, right? So the algebra would be the quiver. So in this case, this is A modules, finite dimensional, and A, well, A is a 5-dimensional algebra. And the basis is 1E, 1, 1 O, 1 minus 2 rho. This is idempotence. E, F, and E, F. This is sort of the basis of this algebra, yeah. So and now the multiplications are, well. I mean we have the idempotent here. We have E going up. We have F going down. So the E would be in A1 minus 2 rho 1 O, and the F would be in A1 O 1 minus 2 rho. And this then form a C basis of my algebra, the quiver algebra, 5-dimensional thing. And now the multiplication you have sort of to figure out yourself, yeah, by these hints I've given. So in case of SL2, this is all sort of very easy and explicit. And when you lose SL2, then hell breaks loose, sort of pretty quickly. No hope to do such concrete things. Yeah. Okay. And now for BGG reciprocity. So for BGG reciprocity, let me give a proof.
Can I ask a quick
Yes.
question about the? So for targeting the SL2, when we have these singular chi, will they always be associated to some parabolic subgroup of the vector, or does the subgroup fixing that would not have to be parabolic?
Well, this is a little bit tricky question, but let me try to answer it. So the point is the following. I mean this category O, this will be composed as some O chi intersect O lambda bar, and here there's some parameter set lambda. I write rho dominant, whatever this is, and all these blocks, all these things are equivalent to integral blocks for smaller Lie cross. Integral blocks of O, yeah, for smaller Lie cross. And for integral blocks, your question is yes. Okay. So if you have an integral block which is singular, then it corresponds to a parabola.
Okay.
Yeah.
If it's not integral, then
If it's not integral, then you have to replace the Weil group by the integral Weil group.
okay.
And then again, it's parabolic, but in the integral Weil group.
Okay. All right, thank you.
Yeah. Okay, so now I'm going for the BGT reciprocity, and now I suppose that you all know about X. So let me. I mean, here is an important fact. Yeah, so it's a lemma or something. Yeah, the X groups inside the category of O of a Werner module and another module, they almost always vanish. So they vanish if I is not 0, and they vanish if lambda is not mu. So the only case in which they don't vanish is if I is 0, they just homomorphisms from the Werner module to the lambda. That's the only case. Let me prove it. Let me prove it. I mean, proof. I explained that this delta lambda has a projective cover, and the kernel consists of some. There is a subquotient delta lambda plus something, yeah, u, and u is a positive root, and not 0. Yeah, so we and now we can continue this way. Yeah, so the Werner subquotients are getting bigger and bigger if we take a projective resolution. Yeah. So in the very least, all so the kernel is here, but also all these guys have only Werner subquotients which are highest weight bigger than none. Okay. Now, if we make homomorphisms of this to delta mu and assume mu is less than lambda. So in the sense of I could write lambda mu is not lambda plus a positive root, a linear combination of positive roots, the sum of positive roots. Then we see that this is true, right? If mu is even different from lambda, then all homomorphisms to delta mu are just 0. Yeah, all these Werner subquotients here have so big highest weight. Yeah, here we have the highest weight lambda, and the mu is sort of sitting below, and then there is just no homomorphism from here to here. And if the Werner is getting bigger, even less homomorphisms. And all these projective modules, no homomorphisms whatsoever. So 0. Everything is 0. If lambda is equal mu, then there is a homomorphism. So one homomorphism from here to here, and all the others are 0. So same. Now, what if mu is in lambda plus r stuff? I should write and mu is not equal to lambda, say. Well, in this case, we take the dual. We have this factor of duality, and then we are safe again. Check. So here, this is one. And so there's just no x between these guys, except okay. Okay. So this is a useful statement. And now let me use it to prove BGG reciprocity. I'll prove it. Um, 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 it is always slightly. Let me see how to how I did trick that. I think the first thing I have to check is that the multiplicity in M of a simple L lambda is just the dimension of homomorphisms of E lambda. Right? Because okay, I mean, I should write somewhere. I should write somewhere that the dimension of homomorphisms of E lambda to L mu is delta lambda mu. Right? I hope this is pretty clear. I mean, this is again a general fact about C-linear abelian categories with these properties we had. So if this so we can make induction of a filtration about the Jordan-Hölder series, we get this equality. We get this equality, yeah. And so and so my computer is up because I mean it's if I recall correctly a slightly tricky argument, and because here we have it. So so what we would need to show is I'm still confused. Wait. It's so I think I could I could try to prove that the dimension of homomorphisms from P lambda to NADLA mu, because it is anyhow the same thing, is the same as the multiplicity of delta mu in a composition series. Lambda. This looks good. So if we prove this, we get this. I mean this I just reformulated like delta mu lambda. Okay. Okay, now I'm in good. Okay. I mean, I would like to even prove this. Whenever I have a module with a delta flag. Delta. Delta flag. Yeah. I'm trying to prove this for any module with a delta flag. But see, if now I can make induction on the delta flag because there is no x between delta and nabla. Right? So I can just this if I have I will get a short exact sequence of homomorphisms. If I split off a delta here. So it will follow if I can prove that delta lambda delta I don't know gamma delta mu is equal to the dimension of homomorphisms from delta gamma to nabla mu. And this is true. Proof finished. Yeah, I mean the whole point was that there is no x1. Yeah. We only need that there's no x1 between different deltas and nablas, and the homomorphisms are only if lambda is equal to delta, and then we can proceed by induction on the delta. Okay, very good. So now what's now wait, I'm confused with the time. No, I have still some time. Now let me before I study this category O thing further, let me make a bit more precise the connection of category O to sort of other parts of what you might be more familiar with of sheath and this kind of thing. Yeah? So the first thing I want to explain is about the relation of O to Chandra model. This is due to Bernstein and Gelbart. And okay, I mean these Chandra modules. I don't want to go into this business too much, but I have to explain a little bit because let's see where it comes from. So the general principle is that when you have a real reductive Lie, G over R, the reductive Lie. And then you have G acts on the Hilbert space, okay? on the Hilbert space, unitary representation. Let's take a unitary irreducible. Yeah. So it's really a continuous action of G on this Hilbert space, which with no proper closing subspaces, yeah, as you expect. So unitary irreducible. And these are most complicated. Yeah, the classification of these things is finished by almost by computer. Yeah, it's quite horrible. It's Bowen who does kind of thing. But what you can then do is take a maximal compact subgroup, compact, and you can get here. You take the k finite vectors. So this is all vectors in H, such that if I apply k to V and take the C span of this is finite dimension, the so-called k finite vectors. And then on these k finite vectors acts the Lie algebra. The Lie algebra of this group. So the Lie algebra of the group G, which is a real Lie algebra, yeah, this acts. And I mean, you know, this is not so evident, yeah, because if a group acts on a Hilbert space, not all vectors have to be differentiable. Yeah, you might imagine, just imagine, you have P1. Yeah, you have say, yeah, I don't know. You have SL2R, and this acts on P1C. Why not? And then it also acts on. Now it's not a unitary representation, but it doesn't matter so much. Yeah. So L2 functions on C1C. Yeah. Finally, this is a sphere, and we know what is L2 functions on the sphere, and so it will act on L2 functions on the sphere, not in a unitary way, but it will act at least at all. But now the Lie algebra need not act at all. Yeah. The Lie algebra wants to act by vector fields applied to functions. And if you have an L2 function, no way to apply a vector field. But now, if we have here the maximal compact subgroup, which is X02 in this case, then this is sort of acts by rotations on the sphere. Yeah, and a vector which together with its rotations spans a finite dimensional vector space. This is called a spherical harmonics, something like this. Yeah? And these spherical harmonics, they are differentiable. Those guys I can apply the Lie algebra. And this is what happens here. It's a sort of great generality. That you can have the Lie algebra act on the k finite vectors. And then, and in fact, also the complexified Lie algebra will act, because it's a complex vector space. And then this is irreducible G K modulus. So it has an algebraic representation of K, so K could be complexified, why not? Yeah. and an algebraic action of the Lie algebra, and they're sort of compatible. And this is these Harishchandra modules. Yeah, I mean, and I mean they're just two compatibilities. One is that the action of the Lie algebra is equivariant for this group KC. This acts by adjoint action on G and X. Yeah. And the other is that if you differentiate the K action, it gives the restriction of the G action. Which is sort of the two obvious compatibilities. Whatever. And I don't want to dwell into this too much, but now there is a special case where this is already a complex group, a sort of complex. And then the maximal compact then the maximal compact is just a compact real form of this thing, yeah? So K is a compact form. And this whole yeah thing here gives G times G modulo. And this is because you see the Lie algebra of G, which is G, is already complex. Yeah, if we start with a complex group like G and C, then its Lie algebra is already a complex Lie algebra. So if we view it as a complex, as a real Lie algebra and complexify it again, it will double. So we get a G cross G module. And this action of K will say us that the adjoint action is finite. So with say the K, so Ek being the diagonal copy, yeah. Okay, and this we can transform this to a bimodule for T such that say at X at G is locally finite. And this is these things called Harishchandra bindings. So let me now put a very precise definition, yeah, because I don't want to. I mean this is. I mean it has to stay a bit a sketch. But now let me make precise definitions. So G is the same as the algebra. And X is a bimodule, so it is a left action, it is a right action. And then we define at say H with bimodule, and we define at X H X H minus H X for X and V. And this defines a new action, defines a new reaction. I mean, this much is true for every Lie algebra. If there's an arbitrary Lie algebra in the bimodule, then we have this adjoint G action. And these Harishchandra bimodules. So Harishchandra bimodules for C. This is defined to be so all bimodules which are locally finite per RGG, locally finite. Now this corresponds to the K. And there should be finite length. And you call these guys A. The category of these guys. And if you try to work with it, I mean, this is sort of the natural thing which comes out from representation theory as I try to roughly explain. But this thing already, to sort of understand what it is, this is very good. Sort of even for SL2, I couldn't do for you these easy arguments that it's for category O. So it's actually much worse. But the theorem is so by theorem. Namely, we have an equivalence of categories from O Z plus we have equivalence of categories to our Chandra by modules, and let's see, we should for every our Chandra bimodule X, we should render it with the dominant module over the U of B. And this will be those Harishchandra bimodules plus. So it will be for all Harishchandra bimodules which are filled by the plus from the left. So sorry, put the plus A times the plus this. So the upshot is that this category in principle is complicated. I mean, even if you want to classify the simple objects in here, it's sort of difficult. And here it's easy. But I did something wrong. I should take here sorry, I should take here the direct sum of all C of lambda, and lambda is integral. Yeah, I should be very careful. I should take the direct sum of all chi. Chi is in the image under C of the integral lists. So now I think my statement is correct. Yeah. Yeah. But so in here, what is a simple object? It's a pretty easy exercise. And in here, it's very complicated. And so this was a sort of a great trick sort of to simplify and also to understand what's happening here. But you see also that it's sort of an unnatural thing, right? It's natural to consider all Harshchandra binomials. And here we only consider those which are killed by the action of the center from the right. I mean, this is an odd part, yeah? And so from the point of view of representation, it's kind of odd. But it's easy, odd and easy. Yeah? So this is the reason we study this. Okay. This is the relation to representation theory. And now I want to discuss the relation to algebraic geometry. Namely, this category O, carried by Z plus, is equivalent to perverse sheaves on V mod V, constant on V orbits. So here the Lie algebra of V is G. Yeah, this is a complex algebra group. And the Lie algebra is the same as the Lie algebra I had. And similar, B is a Borel. It's a Borel. And corresponds to this Borel here. And so this B. My Borel E. And this means sort of smooth along the stratification, I'll say. I say the constant on V orbits, yeah, which is not so nice on V orbits. Okay. And how does this go? How does this go? Well,
so what is the stratification here?
The stratification is a Breuer stratification. So it's a V orbit.
Sure.
Yeah. And this is a slightly bit tricky, because so let me explain what a little bit. The problem is that we have this nice theorem called localization. I don't know how much I should think about. There's something called localization, which is due to Bernstein and Behlendorf. Oh, I turned around the alphabet. Whatever, too bad, that. But I didn't mean that Bernstein is any more in the values on. Which tells us that the category of representations of the Lie algebra G, which are killed by Z plus, this category is equivalent to C modules on U mod. And by D modules, I mean O quasi-coherent, O quasi-coherent D modules on the flag. And the equivalence is just given by the factor of global. Yeah, I mean this is this localization. So well, I mean in principle this is sort of easy to state and more work to prove, but even not so much. So here D is the sheaf of differential operators on the flag variety, which is a sheaf of non-commutative but associative algebras. And this sheaf has for this sheaf of modules, we have, or for this sheaf of algebras, of non-commutative algebras, we have other sheaves of modules. And these are these D modules. But usually you ask in addition that they are O quasi-coherent, because the regular functions or special differential operators are still quasi-coherent. And then, I mean, there is a map from the Lie algebra to the global differential operators on G mod B. Because the group acts on this variety. And so each element of the Lie algebra gives a vector field. Infinitesimal action. And this turns out to be a Lie algebra homomorphism. I hope I didn't screw it up that it's the opposite, but I hope I got it almost, at least. I think it's just true on the marks. Lie algebra homomorphism. And so it passes to the enveloping algebra. And then you have to determine what's the kernel of this map. And you check, and this is some work to do, you check that the kernel is the ideal generated by those guys in the center which kill the trivial sandwich. And so, if I have a D module and take its global sections, I get a module over this ring. And the theorem is that this is an equivalent of cutting. So what did I write? I want to write that this is an equivalent of cutting. Which was a wonderful thing, yeah, because in a way these representations and so on, this is something so non-geometric that it's a headache to work with it. Well, in part, I mean, I hope to have convinced you that to work with category O is not so bad. Yeah, working with D modules is nice geometric, but has also its advantages and disadvantages. I mean, whatever. So we have an equivalent thing. And now certainly we could take here. Well, now there is this Riemann-Hilbert correspondence, yeah, whatever. So we can take here the Hilbert sheaves on G mod B, which are locally constant on the orbits, and they we consider them as a subcategory. Yeah, by Riemann-Hilbert correspondence. And what does it correspond to? Well, and now this is where there is a bit a bad thing. I mean,
Yes, correct. So the time would be up more or less.
aha.
I mean,
Okay.
what you still want to say, just read.
Thank you. Thank you. Tomorrow, Jakob will be away, and you have to take care of me stopping. Sort of. I just realized when it's getting dark.
Or not, yeah.
Yeah, but the thing is that what we get here. So what we get here is finitely generated V locally finite G reps killed by V plus. This is what we get here. And now this is not equal to category O V plus. It's just not because this category O is Z plus. These objects of this category are not killed at the center. Category O does not kill the center, but this does. But happily enough, there is an equivalence. Now this is due to diploma thesis. And this is the end of today's talk. Thank you for your attention.